Good morning, everyone. Today we are going to talk about the Infineon project that we are honored to be on, the Programmable Load Slammer. Here are the distinguished technical directors from Infineon: Yang Zhu, Applications and Product Definition Engineer, and Kumar Gandharva, Applications and Systems Engineer. And we are Team Infineon: Noah Gibb, Computer Engineer and Electrical Engineer, and myself, Abraham DiMartino, Electrical Engineer. Infineon is a world leader in semiconductor solutions, and it was founded in 1999 in Germany when it was spun off from Siemens. It currently has about 47,000 employees worldwide and had a revenue for fiscal year 2019 of approximately $10 billion. It runs 54 R&D locations and has 21 manufacturing locations. We worked with the Rhode Island location, which creates and develops power management products. I am going to start with some background information for the motivation into why load slammers are a necessity in today's voltage-regulated world. These days, most voltage regulators are built onto the same board as a CPU or GPU, but before this can happen, a robust test must be performed to make sure the voltage regulator will be able to meet or exceed the specifications for that GPU or CPU. For this example of the GPU on this slide, going from sleep mode to full gaming mode, the voltage needs to stay constant, but the current being drawn makes it hard to do so. In this GPU example, if it needs a constant 1 volt, and when the GPU ramps up to full gaming mode, its power requirement is 78 watts, this equates to about 78 amps of current draw. This is a current ramp with a very fast slew rate. Typical commercial electronic loads cannot emulate this, and the current draw in some chips can go up to 1,000 amps per microsecond of low transients. Of course, the voltage regulator needs to be tested to see how it handles that very quick change in current, and that is where the load slammer comes in. To achieve our ABO, we need to design, build, and test a single PCB device that is microcontroller based. This PCB needs to be able to slam at least 50 amps at the device under test. It needs to have a built-in arbitrary function generator that can produce arbitrary waveforms of up to 10 kHz. We need a special trapezoidal signal built in that can reach 100 MHz with a buffer of 1 to 2 MHz on the top end. This trapezoidal signal needs to have an adjustable slew rate, duty cycle, and amplitude, and all of the functions need to be controlled by an easy-to-use GUI with data capture in real time. Fortunately, the anticipated best outcome was not reached due mainly to COVID. We had limited time with our TDs, and not being able to collaborate in person hurt the process immensely. Some other factors were the PSOC not having the internal current drive capabilities at the amplitudes and frequencies we needed. The Pol board load adjust was delivering 75 milliamps. The function generator was delivering 15 milliamps, and the PSOC was only delivering 500 microamps. All of these tests were at the 800 millivolt peak-to-peak and square pulse at 5 kHz. We were in the process of adding external components, namely op-amps and a unity gain buffer configuration, to increase drive current. We did achieve control of the PSOC using Python. We had finished the hardware design, and we had a function generator with arbitrary wave generation up to 10 kHz. We also had designed a 1 MHz square wave with correct amplitude. This project will reduce the number of function generators required with today's load boards, a savings of approximately $10,000 for the next few years. This project will also save valuable engineer, technician, and customer validation time by simplifying setup and storing preloaded transient profiles on our demonstration boards. The 3D transient feature will help find weaknesses in designs, further saving validation time and customer relationship impacts due to marginal systems. The field and application engineers will receive these tools to enable customer validation. This tool can enable Infineon's customers with their own electronic loads, which can lead to customers buying Infineon products. Validation time savings, preventing marginal customer problems, and cell enablement could exceed $50,000 annually, which is a big economic impact. I am going to talk about my individual technical contributions to this project. First, the hardware design, testing, and finished schematic. Next, the Pol board, the point of load test board that was used spring semester to test the microcontroller. And last, I will talk about the external components added to increase the drive current of the PSOC. The first component we are going to put in our device was the load slammer. For the hardware design specifications, we needed this circuit similar to as shown. Over on the upper right is the device under test, connected to the drain of the Infineon NMOS. We had to test the full range of possible voltages that might be used. This was designed to be between 0.5 and 5.5 volts. On the NMOS source is where we have the pulse 50 amps. To do this, we used a Texas Instruments operational amplifier and the Infineon NMOS high current component. We had a feedback loop with capacitors and resistors on the op-amp and a ratio of sense resistors on the source leg of the NMOS to maintain the amperage we needed. This was simulated and tested to achieve the desired results. There does not exist over on the left a component called the pulse generator in the real world, so the component that was going to be put there was the PSOC microcontroller. The POL board was a big focus of my spring semester. This board was used to test the PSOC microcontroller's ability to slam loads. It had a slot for the board being tested and a slot for the load slamming board. The load adjust was used to test that the board was working correctly. The input point for the PSOC and function generator only worked if the jumper was pulled out first. The function generator was able to control the load slamming board, but we could not get the PSOC to control the board on its own. So external components had to be added. This will be talked about in the next slide. The external components added were a breakout board with two op-amps in an inverted configuration. Noah changed the resistors on R1 and R4 to 10 kilo-ohm to get a gain of 1. I changed the R8 and R9 to get 800 millivolts for testing on the output. They did not work correctly, and so I hooked up an LM741 op-amp as a unity gain buffer in a single stage and was able to get 13 milliamps of drive current on the output of pin 6 on the op-amp from the PSOC. This was still not enough to control the load slammer board, and at this point I ran out of time for further testing. I would now like to introduce the next speaker, Noah Gibb.
Hi, I'm Noah Gibb, and I'm going to be talking about my individual technical contributions to this project, beginning with the hardware development and moving to software. In hardware, a significant portion of time was spent trying to create an arbitrary waveform generator. Per our specifications, the arbitrary waveform generator only needed to be implemented for a maximum of 10 kHz. The PSOC 5 features the WaveDAC 8 component, which can generate completely arbitrary waveforms using the internal voltage and current sources, but operates at a low internal frequency. By connecting an external clock to the WaveDAC 8, the frequency can be increased to meet our specifications while any arbitrary waveform can be produced. In software, communication between PSOC and Python was established over the USB bus. This allows the board to run at an increased maximum frequency of 48 MHz. In Cypress Creator, the PSOC device is set to loop continuously and open its ports to the USB data bus. The board then waits for a command to be issued over that data bus, which will most likely be coming from Python here, before its pins and memory is accessed and performs a command. This will enable the PSOC to be controlled from the Python-based GUI and allow for parameters to be changed immediately rather than reprogramming the entire board. This approach for Python to PSOC communication requires that the two USB ports on the PSOC are used. When the PSOC is initially programmed, it will need to be connected by its J2 programming USB port, and when communication is established, it will need to be connected over the J1 communications port. This eliminates the need for the Mini-Prog4, a USB serial debugger and programmer that was originally used for this communication. Instead, the PSOC can be directly accessed over the USB bus once the proper drivers are set up. Elimination of the Mini-Prog decreases project cost as well as simplifies the end design as it will use less components. The graphical user interface shown to the right is the Infineon Mini Slammer GUI with the addition of PSOC controls as seen on the far right. The tkinter application is able to program and change parameters on the PSOC board outside of Cypress Creator, its native IDE. However, without sufficient hardware capabilities, software development was slowed due to our need to establish hardware to test it on. Team Infineon would like to thank our great program director, Dr. Sunak, as well as our technical directors, Yang Zhu, Kumar Gandharva, and Danny Clavet, as well as our consulting technical director, Alex DiPetrillo, for their support, guidance, and inspiration during this project. Thank you.